Uh, just a quick revision. We started MR physics by talking about the coils and types of magnet, permanent magnet, solenoid, and superconducting. And we took the basics of MRI, how the protons are the main component for MRI, and especially the hydrogen atoms, and how they are spin and precess, have the spinning and precession movement. And we talked about the Larmor frequency, Larmor equation. And when we make a main magnetic field in MZ direction, and there is also MXY, in which we revert the magnetic field to XY direction for measurement, for its measurement, but the main magnetic field in MZ, when we apply radio frequency pulse, the magnetization pass from MZ to MXY, and then relaxation recovery occur. T1 relaxation or longitudinal relaxation, which aim to measure MZ when it recovered to 63%, and T2 will recover to 37%. We talk about T1 time and T2 star free induction decay. Spin echo, how spin echo depend on 90-degree and 180-degree pulses. And TR and TE, we talked about all of that. T1 weighted image and how it need short TR and short TE, and T2 have a long TR and long TE. And proton density, we cancel effect of T1 and T2, so it need long TR and short TE. This is called conventional spin echo. We also talked about the gradient echo, which depend on radio frequency pulse with degrees less than the conventional echo. Then when we apply slice selection gradient, phase encoding, and frequency encoding gradient. That slice selection gradient, we talked about it, and frequency encoding, the readout gradient, and phase encoding. Then talked about spatial encoding. Now we'll start with the K-space. What is the K-space? As the slice data is collected, it is slotted into T2 representation. T2 representation called a K-space. It's called a K-space. Each column in the K-space represent one frequency encoding step, and each row represent phase encoding steps. So each point in the K-space contain information about the whole MR image. The center contain more contrast information. This is important information for MCQ. The center contrast, important for the contrast information. So data, it include the data from shallow encoding gradient. Shallow gradient represent a gradient with low angle and low spatial frequency, less detail, but stronger signal. And the periphery of the K-space contain the fine details. So the data, it have the data from a steeper gradient with more sharp angle gradient, higher frequency, and had more detail and weak signal. So it is that all raw data stores in that K-space. The center have the long wavelengths, and the K-space periphery have the shorter wavelengths, so it provides the fine details. You don't need to get all data for that to fill that space in order to not to have so much time. So the sequences include radio frequency pulse at 90-degree pulse. At the same time, we apply the slice selection. At the same time of the radio frequency pulse, we apply the slice selection gradient. Then step 3, phase encoding gradient. Straight after the radio frequency pulse, we start the phase encoding gradient. After the slice selection has been completed, after we selecting the slice we need to image in the K-space, we apply the phase encoding gradient. The cycle has to be repeated the same number of times as rows in the K-space for phase encoding gradient. Frequency encoding gradient, timing after each step of phase encoding gradient, we start frequency encoding gradient. Then step 5 is sequence repetition after TR time, the whole sequence repeated again. So radio frequency pulse, this is the up one, the up graph is the for conventional echo sequence, and both these all are for gradient sequence. For conventional 90 and 180, then echo and repeat after TR time. For gradient sequence, we need gradient slice selection, then phase encoding gradient just after the slice selection. Then after each phase encoding, and each which is repeated according to the rows in the k-space, number of row, we apply a frequency encoding, which is the readout gradient, occur at the same time of the echo time. And after that time, we start the sequence again as well. Those the scan time equal TR by number of phase encoding steps by number of excitations. So the timing of the scan depend on phase encoding gradient. The number of phase encoding gradient didn't depend on slice selection is once at the start, and the frequency encoding after each phase encoding. So the phase encoding, the one which depend on the timing. So if we have a typical brain which contain 18 slices, the TR time is 540 milliseconds. In a matrix size 256 by 512. So we have, as I told in the last time, we start in the matrix. We choose the shortest dimension to make it the dimension for phase encoding steps. So we applied in the matrix of 256 applied phase encoding direction. However, the frequency will read the 512. So we need by the end, we need 256 phase encoding steps required per slice. So the scan time is TR time, which is 540, by phase encoding steps, 256, by number of slices. Number of slices divided by 60,000 to make it in minutes rather than in milliseconds. So the net time is needed is 41.4 minutes per slice, per one slice. Okay, these slices, but it says per 18 slices. Okay, sorry, per 18 slices. This is very long scan with a lot of dead time, because after each echo time we wait for a long time till which is called the dead time. It is needed to rephrase the signal to make the protons recover to its normal and natural state after we have been dephased by the magnetic field. So we can start again from zero by 90-degree pulse. So there is a lot of dead time. We can use this dead time by selecting another slice and starting a cycle, then selecting a third slice and starting a cycle. So in 540 milliseconds, we can scan 18 lines of 18 different k-spaces. So we'll recalculate, it will take 2.3 minutes per scan. So we start slice 2 just after echo time, then slice 3 just after the echo time of the slice 2. So within that time, we started the 18 slices by once. Multi-echo signal is another way to save time. We can acquire more echoes in one cycle. So proton density use a short echo time, as proton density use a short echo time, and T2 use a long echo time. So we can use this to make both, and both of them, both proton density and T2 have a long TR. So we can make proton density and T2 once by each other. Okay, so we can transmit two 180-degree pulse to create two echoes with different TEs of the same row of the at the same K space. In this way, we create a proton density and T2 in the same amount of time as they take to create one image. As both need a long TR, so we can use that the concept of proton density need a short TE to start taking a proton density image. Then after long TE, we take the T2 image, and both of them need the long TR. So we take both of them at the same time. Another concept is turbo-spin echo. What is the turbo-spin echo? We can repeat 180-degree radio frequency pulses many times, creating many echoes within one cycle. If we apply a different phase encoding gradient each time, we can fill up different times of K space. The number of echoes we create is called echo train length. So we apply one 90-degree pulse and multiple 180-degree pulses. The echo time here is called T. It's not that echo time or that. It's T effective. T effective is taken the echo created when phase encoding gradient is 0 and is called echo effective. The turbo-spin echo time it will be TR by number of phase encoding by number of slices divided by echo train length. So if we have 16 echo train lengths, it will be divided by 16. It's very fast and can create two images of different contrast, double echo, turbo-spin echo, or we can increase the matrix size by this time. But disadvantage, it will provide a heavily weighted T2 because TR will be very long. TR is the timing between 90-degree and 90-degree. The 90-degree, the timing between both 90-degree will be very long. So it will have a heavy weighted T2 image. And also we'll have a mix of contrast because the echo for that is different from echo of that. So it will be T2. We can't do turbo-spin echo except for T2 because it have a long TR. TR is applicable for T2. Okay, so but this T2 image will have a different contrast, mix of contrast because the changes in TE. The echo time will be changed between slice and slice. Fast advanced spin echo or half Fourier acquisition single shot turbo spin echo, HAST or haste. We only need to fill in this sequence fill up to just half or 60%. Typically, they fill 60% of the K space. These areas of K space are filled, okay, which is called half Fourier imaging. And we extrapolate the rest of K space and complete the image. By mathematically, the rest of image will be created. The very late echoes are put in the center heavily, so it will have a high contrast. Center have a high contrast, so we will have heavily T2 weighted image. It results that images is only free water will be image. So it is the concept for images that we want to image only the water as MRCB. MRCB or MRU or MR intrography, it will be the concept. The practical result of conjugate symmetry is that only half of the K-space data needed to be collected, 60%, and other half is estimated mathematically. Okay, this can be translated to reduction of imaging time, reduced to the minimum time. Okay, as MR intrography, MR heart, MR urography. So we don't need a resolution or other organs. We need only the water within the organ. Other technique is called inversion recovery sequence. What is the inversion recovery? It is inversion used as a variant of a spin echo. It is type of a spin echo, not gradient echo, because it's used 180-degree pulses, radio frequency pulse. They are used to null the signal to complete block the signal from a certain tissue. We don't need in this image fat, so it's called stare. We don't need water or fluid signal, so it's called, we make flare. The first in both flare or stare, we apply 180-degree pulse. Then start the cycle and then flip the MZ through 180 to a negative value at MZ recover at the same point it reach 0 before become positive again if we apply our 90 degree. To make it simple, and as we said in the last time, all protons normally in the magnetic field will be flipping in the MZ direction. So all of them will be MZ. So we'll apply 180 instead of 90. So all of them will be in another direction of the MZ direction, okay? And they will start recovery. When they reach 0 point, there will be no signal within the MZ or MXY. There will be no signal from that organ. So we'll start at that point, at that time, we start to take the image by applying 90-degree pulse and start taking the image. Okay, fat and fluid have different TI. Fat have the fat have short TI and fluid have a long TI. As after a short time, all fat signal will be have no signal, so we can apply flare, we can apply stare, and after a long time, the all fluid signal will be nulled of signal, so we can make the flare. Short tau inversion recovery stands for STIR, the fat signal nulled by selecting 130 millisecond. However, flare, fluid nulled by selecting long TI, 2500 millisecond. Okay. MR angiogram techniques. This is a very important question in written, in short or long, as a short or long. It come several times. MR angiogram technique, we should write that there are two types of MR angiogram technique: dark and light and bright blood. Dark blood, depending only mainly on conventional echo sequence. Bright blood mainly depending on non-contrast, if non-contrast gradient, if contrast or contrast enhanced. Okay, dark blood as fast spin echo, inversion recovery, susceptibility weighted image, non-contrast as time of flight, phase contrast, arterial spin labeling, fast spin echo as well can be gradient or conventional fast spin echo, and steady state free precession or be contrast enhanced gradient. The concept for flow-related enhanced gradient for MR angiography, okay? The result of magnetic saturation, this is the imaged area, this is the imaged area, and these are outside the imaged area, okay? So the tissue around, all the tissue here will be saturated by multiple TR from the gradient applied to this slice selected area. Okay. However, the fresh moving blood within the image slice will not be exposed to that repeated TRs from the gradient. So they will produce more signal. They will have a lot more transverse magnetization, as these are already saturated by the prolonged TR, and but the fresh flowing blood will have more transverse magnetization than the surrounding tissue and return larger signal. Okay, this is the concept as this time of flight in a brain. MR angiography flow void in conventional sequence in a spin echo. It occur only in a spin echo. So in a spin echo, to have a signal, we should apply 90 and 180 degree pulses. The slide, this is the slide being image, and this outside the slide being image. Each tissue within this slide should be subjected to both the 90 and 180 degree radio frequency pulses to give the signal. Okay, so the signal from spin echo dependent on receiving both. Okay, if the tissue in a slab exposed to 90 degree, then move out of the slab, it will not receive 180 degree pulses to be able to generate an echo. Similarly, the tissue moving to the slab exposed to 180 and not exposed to the previous 90 degree pulses. Okay, so if it moves slightly slower, what I say, these tissues of the blood that is moving and exposed to only 180 or 90 degree pulses will not give a signal. It will be dark, it will be black. But if that tissue is moving slowly, slower than TE by echo time divided by 2, some material will be exposed to both 90. It will be too slow, so it will be exposed to both 90 and 180 degree pulses, depending on how much material it remains. So it will give a signal, as in thrombosed blood or slow-moving blood. Okay, atherosclerotic plaques and dissection, it will be like that. This T2 weighted image, conventional spin echo T2, this is the blood vessel appear dark. Also susceptibility weighted image, which also depend on the paramagnetic effect of the oxyhemoglobin in arterial spin labeling. MR angiography spin phase effect, which is called phase encoding gradient. Phase encoding gradient is applied that the gradient apply the phases of processing protons and so localize the location of the signal. Okay, a proton that is moving along the gradient will alter its phase according to the length of time of the gradient is applied, the magnitude of the gradient, and the velocity. So this gradient is applied with a specific time, with a specific magnitude, and according, so it can, the velocity of the protons can be calculated. Okay. Stationary protons, their frequency will be stable. However, moving protons, as the proton move along the gradient, the frequency increase, resulting in increase in phase. These are the three main components used for MR angiography. After the first slide, if you have a question, a long question to write about MR angiography, you will write first dark blood and shorthand for dark blood, and bright blood and you should write full details about these three main angiographic techniques: time of flight, phase contrast, and contrast enhanced. Time of flight is a gradient echo sequence. It uses multiple short TRs, as we said. It can be either in 2D or 3D, and the pre-saturation saturating band are applied, and these saturating band to reduce the signal from the blood flowing into the imaging field from a certain direction. So if we apply it distal to the imaging field to saturate out returning venous flow, but ensure high signal of the outgoing arterial flow. Okay, so we saturate venous signal and ensure that arterial signal will be imaged. It can be used for venous, but more we use it in arterial. And we made it in 3D TOF with very high resolution. It is very sensitive to flow. This is the advantages of time of flight, but have disadvantages as flow-wise due to implant saturation. Maybe an artery coming in the same direction, and a small artery coming in the same direction of the vein, it will be saturated. Post-stenotic turbulence, distal to the stenosis. Any distal to the stenosis will be turbulence, and it will give a bad image. It can exaggerate the length of occlusion and stenosis. It is sensitive to metal artifact. It have very high T1 signal from stationary nuclei, which is the main defect in the time of flight, will be visible as hemorrhage. Hemorrhage will be visible. And retrograde arterial flow may be obscured if venous saturation band have been applied. Phase contrast is depending on bipolar gradient. We use in phase contrast bipolar gradient to exploit the differences in transverse magnetization, and it's mainly or only used in 3 dimensions. Unlike time of flight can be 2D or 3D, but phase contrast is 3D. So the importance of this bipolar gradient advantage to control the velocity dependent phase shift to alter the sensitivity to different flow velocities. And velocity can be quantified as well as the direction of the moving blood, and have better background suppression. It's insensitive to T1 effect, unlike time of flight. The disadvantages, it take 4 times as long as time of flight. Time of flight is a long technique, not a short technique, but phase contrast is 4 times long than time of flight. Okay, because it requires 3 orthogonal direction to create an image. It is more sensitive to turbulence, so it can make motion artifacts. Okay, contrast enhanced, it is 3D spoiled gradient. Use 3D spoiled gradient. You should use gadolinium chelate, and the area of interest being imaged in the first pass of contrast to ensure best signal. It has advantage being more accurate, reproducible, faster scan, and can be imaged in pre-arterial and venous contrast, have fewer artifacts and better signal. Because of the contrast, it has a better signal and spatial resolution, but it is not flow sensitive. It can give false negative because of enhancing thrombus, can be enhancing thrombus rather than free flow. Okay, this is MRA of the brain of time of flight, and this is MRV of the brain phase contrast, using phase contrast technique, and this mainly contrast enhanced used for arterial aortic angiography, contrast enhanced. This is MRA time of flight, showing the stenosis here clearly visualized. Diffusion weighted image. Diffusion weighted image is using also gradient echo. It is play of gradients. The diffusion weighted image measure the thermal Brownian motion of water molecule. It requires fast imaging sequence of such as the gradient echo. Okay, we use 2 strong gradient pulses of magnitude of a certain magnitude, duration, and separated by a certain time interval to produce that. So the moving blood will have a phase shift and low signal, and the static or restricted diffusion area will be unaltered and will give more signal. Okay. All diffusion weighted image are T2 based. They are T2 based images. Okay. How much an image of diffusion is measured? It's measured by something called in term of B factor. B factor 0 means no diffusion weighted image. It is a T2 image. Okay. When we increase it, we increase the diffusion. Okay, it can be more than 1,000 seconds per millimeter square, which is heavily diffusion weighted image. There is also apparent diffusion coefficient. This is B0, this is B1000, this is ADC map, or apparent diffusion coefficient, which is the measure of magnitude of diffusion and remove the T2 effect. It measures the diffusion and remove the T2. So it is the reverse of that of B1000. Low ADC means restricted diffusion. High ADC means normal diffusion. So the ADC is a calculated image, is a mathematical or parametric map. As in this case, with the diffusion restriction in the brain, secondary to infarction, it shows high signal in B1000 and low signal ADC map. If there is high signal in both, then it will be a T2 shine through effect. So we should check both of the ADC and B high B value to to say that there is restricted diffusion rather than T2 shine-through effect. Okay, diffusion tensor imaging and fiber tractography. So the diffusion gradient can be increased from 3 to up to many more. We used in diffusion and the normal diffusion 2 diffusion gradients. Here we used from 3 up to many more. With increasing scan time, each diffusion increase, it would increase scan time. So it will give us a calculation of ease of diffusion in different direction. Diffusion tensor imaging. This tensor used to show the direction of diffusion in a white matter tracks and assess their integrity in color-coded fractional anisotropy. Fractional anisotropy which is the measure for white matter tracts integrity. On the color-coded fractional anisotropy map, the fiber passing from superior to inferior will be in blue. In blue as projection fibers. Projection fibers is corticospinal tracts. Corticospinal tracts are blue. Fibers passing from right to left are colored in red as commissural fibers, or corpus callosum is the main commissural fibers in the brain. And fibers passing from anterior to posterior are coded in green, which are association fibers, which is passed from anterior to posterior. By joining these tensors together, making a 3D model of the fiber called tractography. We have also perfusion weighted image, which use information about blood flow to generate maps of different perfusion parameters. It can be contrast enhanced, so it uses rapid acquisition of the gradient echo, T2 star image, so repeatedly acquired after pulse of gradient of gadolinium contrast, causing susceptibility in induced signal, and it should be performed in T1 because of the contrast. And without contrast, we can make perfusion weighted image by the arterial spin labeling, which use the natural motion of spin in arteries to generate perfusion maps. Functional imaging, which is called the blood oxygenation level dependent. Bold images, you will hear that also in the brain, depend on that oxyhemoglobin is a diamagnetic, have weak magnetic properties. However, the oxy is a paramagnetic and cause magnetic field inhomogeneity. When we apply stimulus, such as talking, we need to examine the talking center in the brain. We apply a stimulus of talking. So it increased when the case talk, it increased the vascularity, so it increased the oxy and also the oxyhemoglobin in that area, and take image before and after stimulus and subtract each images and see the stimulus, how it altered the brain. Proton MR spectroscopy. It uses hydrogen MR spectroscopy focus on carbon-bound proton in 1 to 5 parts per million range of chemical shift scale. It can detect metabolites that are present in high enough concentration within micromolecule per gram range and mobile on the MR spectroscopy. This line is the most important. It needs strong uniform 1 part per million magnetic field to get a good signal. This is very, very frequent in MCQ questions, that MR spectroscopy needs a uniform magnetic field and high strength magnetic field of at least 1.5 Tesla. Okay. Techniques of pressed point resolved spectroscopy and stimulated echo acquisition mode STEAM are both the most famous techniques to make spectroscopy image. It helps to assess the level of metabolite in a normal and diseased tissue of the brain. In many tissues rather than brain, but the most frequently used is for brain. So apply a ROI, or region of interest, a small area in the brain. The normal one will give this ladder appearance of choline, creatinine, choline, and sodium acetyl N-acetyl aspartate. This is the lowest for choline, creatinine, then higher for choline, then N-acetyl aspartate would be the most highest peak in a normal tissue. This ladder or step ladder appearance will be altered in diseased brain. As in here, choline is higher than NAA and creat, and here also choline is higher than NAA and creat. Another entity for contrast study or other types of magnetism. Magnetism can be ferromagnetic as iron, nickel, cobalt, or super paramagnetic, which contains some elements of ferromagnetic material, paramagnetic, that increase T1 and T2 relaxation. We'll see how, as in oxygen, magnesium, or gadolinium, or diamagnetic, which have weak repel of magnetic field as water, copper, and nitrogen. Okay, this is a ferromagnetic effect of foreign bodies. This is the concept of paramagnetic, the paramagnetic material as oxygen or gadolinium here. This is in a tissue with a long T1. This is the, as you remember the last time, this is the T1 graph, and this is the T2 graph. T1 graph, rising curve, and this exponential curve. The rising curve for T1 will be shortened by the effect of that. It will short T1 and short T2. The effect of contrast will make T1 shorter because of increased relaxation. It increased the relaxation of protons, so it have a short T1 and short T2 time. In T1, as you see, when time is shortened, it will have a higher signal. But in T2, when it is shortened, the time is short, but lower signal, smaller signal. That's why we use the T1 in contrast and we don't use the T2, because T1 with contrast will give a bright signal, but T2 will give a dark or lower signal. And also it can fast the acquisition time. It will reduce the TR time. Gadolinium, which is gadolinium diethyl nitriamine pentaacetic acid. Gadolinium by its own is toxic, so it should be chelated with another chelating agent as DTBA in this, for example. It must be encased by another molecule, not to cause harm to the body, as the most common one is the nephrogenic systemic fibrosis. When the patient have free gadolinium, it can subject the kidney to nephrogenic systemic fibrosis. It is mainly extracellular in the blood vessels, not enter the cells, and can be imaged dynamic in arterial, venous, or equilibrium phases. I think this with breast cancer and heart showing the contrast. There is other hepatobiliary agents. It include magnesium, which is also paramagnetic magnesium, such as mangafodbir, trisodium, or gatopentate dimeglumine. It is intracellular. It is taken only by functioning hepatocyte in a healthy liver tissue. Okay, but it is very slowly taken by hepatocyte and can be imaged up to 24 hours later. After 24 hours, can be imaged. It doesn't allow for dynamic. We can't image arterial, venous. So it's mainly used for hepatic imaging, as in this case, there is increase of the hepatobiliary agent taken by the hepatocyte. So there is increased visualization of the cancer. The cancer will appear low signal, and the liver will take the contrast and will be high signal. The most commonly used in liver for imaging more than that hepatocellular agent is T2 superparamagnetic contrast. This is a contrast, but an iron oxide contrast as superparamagnetic iron oxide and ultra-small superparamagnetic iron oxide agents. As we said, the iron have a superparamagnetic, oxygen has superparamagnetic character. So they doesn't leak to the interstitium, but it remain in intravascular space until it is eliminated by reticuloendothelial system. So they are taken by the reticuloendothelial system, which is present normally in a normal tissue of the liver, coated with substance to increase uptake by the reticuloendothelial system. But so it reduced, as we said, any contrast agent will reduce signal in T2. It reduced T2 signal of absorbing tissue, which reduced the T2 signal, but it require 1 hour before image acquired. But after 1 hour, the normal liver tissue will be of reduced signal, highlighting the cancer in the liver. This focal lesion of the liver will be brighter than the contrast uptaken normal liver. Okay, except for focal nodular hyperplasia, it will take the reticuloendothelial system contrast agent, and it will be just like the liver. Okay, this is the last slide. Yes, this is the last slide for today. We can, if anyone first has any question, please write in the chat or speak, open the mic and speak, please. And if you want to have 1 or 2 MCQ questions, but first, if you have any question, please tell me. And this is a form. Please fill the form before going. Okay, let's make this MCQ regarding MRI imaging, which is not true. Okay, gadolinium is a superparamagnetic agent. Iron oxide result in signal loss in normal tissue on proton density or heavily weighted T2. Gadolinium cannot be excreted by the body in its pure form. Flowing blood usually appears dark with a spin echo sequence. Iron oxide is the contrast agent of choice in liver imaging. What do you think is not true in these 5? You can write in the chat, and please tell me if you want me to repeat anything. Please tell me.